Uh, uh, Good morning, everyone. Thank you for taking time to attend this presentation. My name is Syed Bokhari. I work for Fidus Systems in Ottawa, Canada. And today I'll be talking about optimization of chip package together with the PCB uh, for, for improving the performance of the system. So let's start with a simple question. This is something that is reasonably well known, but the impact of these assumptions is quite significant. I'm especially focusing on frequencies that are extremely high. So the current state of the art in PAM4 signaling is about 224 plus gigabits per second. So at those high frequencies, we're talking about Nyquist frequencies in the range of 60 gigahertz, and some things that we tend to take for granted are become important. So let's start with a simple question. If you're given two 50 ohm cables, just blindly, without asking what those cables are, and if you connect them together, will the impedance of the new cable be 50 ohms? Questions. Now, what kind of answers? Think of an answer. There are possibly three answers to this question. Some of you would choose to say yes. Some may choose to say no. And a more diplomatic answer would be, it depends. Now, we'll rephrase this question differently. So just keep this in mind. Now, let's do a simulation. Instead of telling you the question in terms of the cables, say, I'll give you two S parameter files. I'm telling you that they belong to different 50 ohm cables. And I'm asking for a simulation, run a simulation. And from the simulation result, can you tell me if the impedance of the cable will be 50 ohms? So let's see what a simulation would do. A simulation would hook them up in cascade. As their S parameter files, easy to hook up in cascade. You cascade two 50 ohm S parameter files, you will get a 50 ohm impedance. There's no question there. So the answer from the simulation is unique, but the answer without looking at the simulation can be very different. And here's the reason why it will be different. Those who said yes would have probably imagined the cables are identical. That's a good assumption, and otherwise you can't connect them easily. So the two identical 50 ohm cables hooked up together would give you 50 ohms. Simulation will also show you 50 ohms. There's no question there. Those who said no probably assume that in general, two 50 ohm cables don't have to be identical. You can have a very thin coax and you can have a very thick coax too. So in which case, even if you succeeded in mating them somehow, there is an impedance discontinuity at the junction, and that would not necessarily give you 50 ohms or a very wide frequency. So that would be the reason why you'd say no. And those who said yes, it depends would be like, okay, you can't just join two cables together. And so you'll need some kind of a taper mechanism. Once you introduce a taper, it becomes it's a question of frequency dependence. At certain frequencies, it'll still be 50 ohms. At very high frequencies, it won't be so. So all three answers are different. But note that the simulation, the answer that you get from simulation is always unique, and that says 50 ohms. So what do we learn from this? If we simplify S parameters of cascaded networks, the theory is fairly accurate. It becomes an approximation in the electromagnetic sense. So you cannot blindly apply cascade theory without really having an idea about what the physical problem looks like. And this is one important thing to remember about cascading S parameters. It's a great tool. It simplifies a lot of things, but there are frequencies where, especially the very high end, it introduces an error. The next thing that we notice is when you simulate a complex structure, we need to, in order to obtain impedances, we need to define ports. Ports have to be placed at some points, and they cannot be placed arbitrarily, especially it is good to place ports at a uniform transmission line section. So, and where you place the port, it should be uniform in both directions from of the port. And that is probably the most ideal location for a port. You can, in theory, place a lumped gap port anywhere you please. But for very high frequencies, it should be at a place where the fields are well behaved, and best at a transmission at a transmission line location. So with these two things, so let me start my presentation on chip package interconnect optimization. The prelude was mostly to lead to exactly what is being done here to optimize a chip package interconnect. Now, again, like I mentioned, I'm talking about really, really high frequencies. Nyquist are in the range of 50 gigahertz plus. That's where these approximations that we generally take for granted become questionable. So what am I optimizing in this chip package interconnect? It's S parameters, obviously, it's S parameters. Now, most of the S parameters that we really care about are the insertion loss, the return loss, and the crosstalk. As far as the insertion loss goes, there's very little one can do about it, especially when you are dealing with a system that has constrained. On a package, there are limitations on how thick or how wide a trace can be, and how lossy. What is the loss in the substrate? Let's assume you pick the best of the best. Your insertion loss is going to be limited by the trace length, trace width. Not a lot you can do there. Return loss, on the other hand, is significant. Return loss affects the insertion loss deviation. And so it is really critical that you optimize the return loss as best as possible so that the insertion loss is smooth and helps in error-free transmission. And we also have a category of crosstalk. I'll not be addressing crosstalk here. Crosstalk deals with a system of nets and how you isolate them. So that's not being considered here. So the focus is primarily on return loss of a very high speed data transmission. And the simulations, again, are done using ANSYS HFSS, which is a 3D, the full 3D EM solver version. So let's take a look at what a package looks like and how we simulate a chip package. This is a typical package. It's one of the more popular ones. There are other types of packages too. This is called an organic package, and it comprises of a core, a thick core, and a number of pre-preg type layers. And its typical structure, it's a flip chip, so there are solder bumps on the chip on the die side, and BGA balls on the PCB side. If you look at this package closely, for most applications, we generate the S parameters of this package by simulating the circuit that I've shown here. Ports are placed on a reference plane, usually on a reference plane that is defined on the die side, and another reference plane on the package side. Ground balls provide the return path continuity on both sides. And this is generally simulated. And this works very well for even up to 25 gigahertz. So, but as the frequency starts increasing, this approach gives you the S parameters all the way up to the BGA balls. The package eventually needs to get integrated with the PCB. The PCB itself would have pads that will connect to the balls. So at the interface between the package and the PCB, there is a discontinuity. So if you notice here how the ports are defined, the ports on the die side, on the die bumps, these are very small. Typically, they are like 35 microns in radius, maybe 90 microns in height. For the frequencies we deal with, it is acceptable to use the S parameter, the port definition, by placing the port on the die on a die bump without sacrificing the accuracy too much. Otherwise, it gets extremely complicated to have a port on the die, within the die, going inside the die. So this is acceptable because the structure is small. But when we look at the BGA bumps, these are typically they could have a pitch of 1 mm. They're about 600 microns tall, about 500 microns wide. These are big structures. And placing a port at a reference plane near the BGA balls to the PCB interface is questionable. This will violate some of the fundamental limitations of S parameter definition. So, but yet this is how, when we ask for a package model, S parameter model, this is what is done, and they give us this model, you take this model and you integrate with the rest of the PCB and proceed. It's good. It's a very good approximation up to fairly high frequencies. But if you're talking 50 gigahertz plus, the approximation tends to break down, and you'll need to consider the entire structure as a whole. Now, here's what a composite chip package PCB stack up looks like. You have the package stack up is different from a PCB. The PCB generally has the mix of layers, prepregs, cores. In packages, it is inevitable. The use of multiple levels of blind vias becomes inevitable. So you will have a number of what in the PCB terms we call as prepreg layers. There's usually a rigid core to provide rigidity to the package, and on both sides of this, you have a number of prepreg layers which are connected by stacked microvias. Depending on the fab that is used, they may have limitations on how many blind vias can be stacked. Usually it's 5. You can't stack more than 5, but that's a package fab dependent thing. So within those limitations, we go ahead and design a package, and then we interface the package to a PCB. At the frequency that I'm talking of, we wouldn't not normally use back drilling on the PCB. It'll be a blind via as well. And we consider this in our example for illustration, we just use the few layers at the top of a PCB to get the interconnect optimized. Now there are sections here. Now, before we start a full-fledged optimization, it's a tedious exercise. There are way too many variables involved. So it's a good practice to section the complex structure into pieces. Now, one of the things we saw in the previous slide is stacked vias. Stacked vias typically have a geometry like what I've shown before. We assume that this is a uniform stacked via geometry, and we optimize this individually so that we can see we can then put them together and redo the final optimization. So if you look at this example here, we have just a stacked via geometry with ground vias on the sides. It's a nearly perfect coax, you could call it. And the simulation with some optimized anti-pad diameter and the location of the ground vias at a particular radius gives us a 40 dB type return loss, even up to 100 gigahertz. So this is probably the easiest of the structures in a complex package. The second one is the core via. That's in the rigid section. It's much longer than the microvias. Again, it can be optimized to a certain extent. It's not as good. The results are not as good as the ones for a microvia, but you can see that you can still do fairly good up to 60 gigahertz. You can do better than 30 dB return loss up to 60 gigahertz. The last part is the BGA vias. Now here is, this is the bottleneck. Now here is where you have very little or no control here on anything. The BGA locations are decided by the pitch of the package. You only have at most the anti-pad on the package side and the anti-pad on the PCB side. Pretty much those are the only two variables. You could have some more ground vias on the package side, but not on the PCB side. So with this one, and here you can clearly see that it's almost impossible to get anything better than 20 dB return loss beyond about, let's say, 30 gigahertz. Okay. Now, if we put them all together, and so we want to optimize the entire structure, we need to integrate all of these pieces together, and we need to change the variables, like we vary a few variables to get the best return loss for the entire structure, which is an integration of the package and the PCB. One thing that we look for is the TDR of this package. We try to get a TDR response that is inductive and capacitive alternatively, so that they tend to cancel out and give us a broadband impedance. And this can be done in many ways to obtain this kind of response. We can vary the inductance. We can make one side more inductive, the other side more capacitive. It is to strike, we need to strike at a balance where it gives you the optimized structure. So if I show you the result over here of a geometry that is optimized, so we have used the piecewise optimization idea. So each one is optimized individually, and then we put them all together and optimize the entire structure as a whole. So this way we keep the number of variables at a smaller value, and it limits the number of trials you need to do for a full 3D HFSS optimization. And as you can see the result, you can pretty much see that we could potentially get a desirable 20 dB return loss up to perhaps up to 30 gigahertz. Beyond that, it is largely taken over by the BGA ball pitch and the size of the BGA balls. And clearly, this represents a limitation in the best return loss that you can get in an integrated chip package structure that uses a 1 mm pitch BGA. If we reduce the pitch of the BGA, like some of the packages that do the very high speed PAM4 200 plus gigabits, they're likely to use the 0.5 mm pitch BGA. This response will improve slightly, but it can be improved to a slightly higher frequency. But essentially, the limitations come from the BGA balls. So with this, so this result tells you that first of all, you do need to integrate the package and the PCB to obtain results that are results that are accurate. If you notice here in the structure, we have transmission lines at both ends, and that's where we place the ports, wave ports in this case. So that removes the error introduced by placing ports at discontinuities. So we get these results will be extremely accurate and would be easily reproducible by a measurement. So with this observation, I'll come to some conclusions here. So when we're dealing with complex structures that comprise a board and that comprise a PCB and a package, we should review the complex structures visually before and decide where to place the ports. Ports are best placed at uniform transmission line sections, and that's where what gives us the best accuracy. So in this case, it's fairly straightforward. Place the ports at the transmission line ends. We don't have to go deep into the die section because the die is electrically much smaller, even at 60 gigahertz. So we could choose the transmission line on the package and place ports at that location. On the PCB side, best to place the ports at the PCB trace location. Now, the optimization exercise can be daunting because there's way too many variables. There's a PCB side and the package side. So it is easier to optimize the individual sections of each discontinuity, like the core via, the blind via, the BGA balls, and even the transmission line. You could design the transmission line to give the desired impedance. Optimize them individually, use them as a good starting point to optimize the end-to-end structure. And you perform the full optimization of the end-to-end structure. With this, I will stop my presentation. If you have any questions, I'll be happy to answer them, or you can reach out to me on using my email. So thank you again for attending the presentation. And